Howdy, folks. I'm going to try to make a quick run through the basics of momentum and what I call interactions, which can encompass when objects collide or push off of each other. So let's talk about momentum. Momentum, by definition, is simple. There is a momentum of a definition of momentum, which says that an object has a momentum p equal to the product of its mass and velocity. Well, a couple of intricacies. Momentum is a vector because velocity is a vector. And so this object has a momentum to the right because it's moving to the right, which is different than a momentum to the left. All right, so the vector nature of momentum is really important. Momentum's units are nothing too fancy. They're the units of mass, kilograms, times the units of velocity, meters per second. So units of momentum, kilogram meters per second. And that's it. That's the definition of momentum. It is the vector, it is a vector. It is the product of mass and velocity. People will tell you fancy phrases. Those are phrases. This is the definition. Okay? Okay, that'll do. So an object can have momentum, and changing an object's momentum, well, the act of doing that requires something. The fact that momentum changes, that's called impulse. All right, so J, we use the variable J to mean the change in momentum. That's also a vector because momentum is a vector, and therefore a change in momentum is a vector. So if this object has a mass m and velocity v, or a momentum p to the right, well, let's say, what if someone were to apply a force to this object like that? We'll call that F net. All right, that's the net force acting on this object. All right, this vector p to the right is not supposed to represent that momentum is a force because it isn't. But this object is currently moving to the right. But there's a force exerted on this object to the left. And let's look at this force as a function of time and what that does to momentum as a function of time. Well, the deal is, via Newton's second law, we can say that A, acceleration, is net F over m. Okay, and we can say that, well, acceleration is the rate of change of velocity, net F over m, and vector, vector. And note here that if we multiply both sides by m, we get that, that net F is m delta v over t, and that m delta v, well, note, because momentum's definition is product of mass and velocity, if we have product of mass and change in velocity, that is delta p. So Newton's second law can be written in a way that says that net F is the rate of change of momentum. Okay, in this case, if we choose a convention where we say to the right is positive, this object is moving to the right initially. Initially has a positive momentum, but let's say there's a constant net F to the left that's negative. All right, well, what does this object do? This object, by definition, well, look, we can talk about how much its momentum must change. Right? We can say from here that delta p, if we multiply both sides of this expression by delta t, we can say that, well, how much will an object's momentum change? That depends. What is the net force applied to the object and for how long? Okay? And so this says that, well, we can write impulse now a couple of ways. Delta p, we've said, is m delta v. But we can also say is F times delta t, and vector, vector, vector. Okay, so this object has a constant negative force applied to it for some amount of time, let's say delta t, and therefore has some change in momentum. And so because there's a force applied in the negative direction, there's got to be a, well, notice this is negative, so delta P over delta T is negative. This object does this, changes momentum at a constant rate, a constant negative rate. And so if we apply this force for long enough, and depending on how massive the object is and how much time passes and how strong the force is, this thing might, at this instant, here's P instantaneous, that says INST, of 0, this force might be exerted for long enough, or the force might be strong enough, or, well, the combination of the force applied and the amount of time that force is applied is enough to make this thing, well, for sure slow down as P approaches 0, maybe stop instantaneously, and then maybe speed up in the negative direction, right? So it's possible that that happens. We can't tell just by looking at this FT graph if the product of F and T is big enough to change this object's momentum all the way down to 0 and then turn it back around, but it could happen. All right, what is for sure the case is that since net F is constant, we get a constant rate of change of momentum. Notice constant rate of change means that the slope of this line is constant, right? The slope of this line is the rate of change of momentum. All right, so a couple things we need to be able to interpret. One, as we just said, the slope of this line is the rate of change of momentum. That is F net. Notice I've written net F, and now I'm saying F net. That's okay. Same thing. All right, the slope of that line is F net. And over here, this FT graph, well, F times delta T is this area, right? This area is F times delta T, and that is the impulse. All right, so this is very common to see that we need to interpret these FT graphs to give us impulse. Okay. Okay. Now, momentum is used a lot when we investigate or when objects interact with each other. And what does that mean? Well, let's take a simple case where this object, well, let's take maybe not a simple case. This is some object of mass little m. This is an object of bigger mass big M. And this thing, let's say, is moving like this. And this one is, I don't know, who knows, moving like that. But let's say faster, why not? None of these things matter because, let's do this. Let's call this 1 and call this 2. And let's look at the forces exerted on each one by the other. All right, so in blue, I'm going to do F on 1 by 2. In red, I'm going to do F on 2 by 1. All right, so I'm using a notation where I mean on by. Okay, so, well, let's again call this the positive direction. Mass 1 is moving in the positive direction, but when it interacts with mass 2, there's going to be a force on mass 1 that points to the left. Okay, so I'm going to draw this part. This is during interaction. We can do a look at a free body diagram for mass 1, and there's going to be a force like this on 1 by 2. There's going to be a force like this on 2 by 1. And Newton's third law says that these forces are equal and opposite. So this force, let's see, on 1 by 2 is going to point in the negative direction. And let's see, they're going to interact now. So here they are moving along. No interaction. They're not applying forces to each other. And let's say that this force that's exerted on 1 by 2 looks something like that. All right, it takes some time for these objects to interact. They don't interact instantaneously, right? This is some time during which, so this is the interaction. Interaction, it says interaction interval, delta T. Okay, well, what happens to object 2? Object 2, well, look, it's more massive, and it's moving faster, and who cares? Because none of that matters. What happens is these two, well, yeah, sure, I'll just try to do my best. These two forces, as functions of time, vary in exactly the same way. Newton's third law requires that to be the case. It doesn't matter anything about these two objects, how fast they're going, what direction they're going, how massive they are, what color they are, if one of them is funnier looking than the other one. None of that stuff matters. What matters is Newton's third law dictates that when objects interact, the forces they exert on each other are equal and opposite. So note, there is an area defined by this ft function that looks like that. There is an area exerted by this, or enclosed by that ft function that looks like that, and those two areas are equal and opposite. And what we're saying there is, well, first of all, we have this f on 1 by 2, and that's equal and opposite to the force exerted on 2 by 1. And these two amounts of times over which these forces are exerted have to be equivalent. We can't have one exerting a force on the other while the other isn't applying a force to it. And what have we just said here? Well, we have just said here that this is delta P1. It's a force exerted on 1. That's going to make number 1's momentum change. I should vectorize these, right? This says that delta P1 is negative delta P2. And this says that the net delta P of the system is 0. And this says momentum is conserved. All right, so what may happen, what definitely does happen, is that each part of this system, when objects interact, each part of this two-object system, each part will change momentum. But the sum of the changes of momentum of the whole system is nothing. That is because, quite literally because, the forces that objects exert on each other are equal and opposite, and that happens with the same amount of time. So it says that these two impulses have to be equal and opposite that objects experience, right? And again, that has no bearing whatsoever on anything to do with either object. It has no bearing on mass or speed or direction or blah, 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 blah. That is always the case. Okay, it is always the case that when objects interact, the system's momentum is conserved, is constant. Okay? Now, as an add-on to that, I'm going to start from what we just said. So I'll say when objects interact, a couple of things. One, I mean, the big one we should always state is momentum is conserved. All right? And there are I mean, the basic way to approach a problem like that is to say, well, that the net initial momentum and the net final momentum of the system are equal. And then we would say, this is, well, usually we would do this. Here's the first object's initial momentum. Here's the second object's initial momentum. Here's the first object's final momentum. Here's the second object's final momentum. All right, and we would start with something like that where we would be careful with direction. Okay, so I would say something like, let's assign that way to be positive, let's assign that way to be negative, and we might have, you know, pluses or minuses here to account for different directions of different momenta. Okay? I will refer you to, I'm not going to go through problem solving here, but you know, this is sort of a review, so I'm hoping that that's something you can go and find evidence for in your own solutions where you've effectively used sign to denote direction. What I want to pick up from, though, is another way of saying this, like we said before, is that delta P1 and delta P2 are equal and opposite. All right, vector, vector, which means, like we said, that the net delta P of the system is 0, vector, And well, then we can say the net delta P. So we can say that the net M delta V of the system is 0. Well, and guess what? The net mass of the system is always the same. That's the definition of a system. We're saying here are the things that we are including as a system, right? So this says that delta V of the system is 0. So that's an important fact, especially as it pertains to College Board. College Board really seems to dig this. So if we say that delta V system equals 0, right, what we're really saying is at any instant, right, there are objects interacting with each other, but the two forces they exert on each other are equal and opposite. That's like saying, right, we're saying that the net force exerted on the system is 0. That's like saying that the acceleration of the system is 0. That's like saying that the system's change in velocity is 0. And when we say the system's change in velocity, we call that, so V system, we call that V center of mass. I'm letting that sink in for a bit on purpose, yes. So what we are saying, or what College Board really likes to talk about, is that delta VCM is 0. So here are three things. 1, 2, 3. That a system's center of mass velocity will not change. A system's center of mass velocity will not change. Watch this. Here's the simplest evidence of that we can give. Here's an object of mass m. Here's an object of mass m also. All right. This object happens to be moving at a speed v. This object is not moving. Okay. This system's center of mass is right there. It's halfway between them. These are two equal masses. So yeah, that's where their center of mass is, right? Well, by the time this one here gets to where this one is, gets to here, here's now the two masses, right? Well, that object went this far. The center of mass went this far, because the center of mass is now right there. So the center of mass went half as far as this mass did in the same amount of time that this mass traveled that distance. And therefore, VCM is this V over 2. It traveled half the distance in the same amount of time that mass m on the left traveled that distance. Agreed? You know what happens when these two things collide and interact? Well, we could very accurately predict that if we use our basic M2 V2 initial, our basic conservation of momentum expression. And so watch this. If these were to hit and stick, very common thing to say, what we would do is take this right side and say, well, the two objects together move at, that's not a 2. These two objects together move at some common final velocity. Right? This goes because that. This is simply mv. The two masses together, we mandated they have the same mass. And there's VF, and there's a common factor of m on both sides. And look at this. The system's final velocity is v over 2. Well, it has to be, because the system's initial velocity was v over 2. Right? Note that these two velocities are the same exact velocity. Now, it's easy to predict when we say hit and stick, but guess what? This doesn't matter at all either. What kind of interaction is it? Do these things hit and stick? Does one bounce off the other? Is this some sort of glancing collision where, maybe this thing comes in like this and ends up bouncing that way because the other one bounced that way? None of that matters. What is always true is that if this system's initial center of mass velocity is something, well, then its center of mass velocity is always that something. And the reason is because, well, the net force exerted on the system is 0. And that's because the two objects exert forces on each other that are equal and opposite. right? So because of that, systems, when they're isolated, they don't accelerate, right? Parts of the systems can accelerate, parts of the systems can change momentum, right? But the system itself does not change momentum. Momentum's conserved. We're saying lots of things. I mean, lots of different things that all mean the same thing, or come from the same reason. All right. But as far as College Board really likes to say, a system's center of mass maintains a constant velocity. Okay. That's another way of saying that momentum is conserved. That's another way of saying that objects experience equal and opposite impulses when they interact. So being able to juggle through lots of different ways of saying the same thing is, well, takes some deep understanding, but it's awesome that it all connects. These things all connect to each other. Okay, so I don't know how much quicker I can do the basics of momentum. Whew! Hope you enjoyed. Goodbye.